Okay, so we're moving into Chapter 7. Chapter 7 deals with modeling with differential equations. So let me give you a moment to copy. No, Clea, we will will be getting into integrals in section 7.3 with separable equations. We will be getting integrals are never going to leave you, but a good question. All right, let me give you a moment to copy this example down, and then we'll talk about it, okay? Okay, so let's see what's going on here with this problem. Let's see what's going on with this problem. All right, so it says, and I'm getting used to this new thing I have for the writing. For what values does e to the rx power satisfy this differential equation? Okay, and this differential equation, of course, can be written equivalently like this. Okay, now the reason we call this a differential equation is because it's an equation that has derivatives in it. It's an equation that has derivatives in it. And whether you use Leibniz notation or Newton's notation to represent the differential equation, it's an equation that has derivatives in it. And a lot of applications in science, engineering, mathematics, economics, biology, and so forth, a lot of applications, you can model the applications with differential equations. So to help you feel a little bit comfortable about like using a differential equation, this little exercise says, it's saying that y equals e to the rx power is a solution to this differential equation. But the thing is, we don't know what r is. So when it says for what values, it should really say for what r values. Okay, so let me ask you this. Let me ask you this here. If, let's say you had an equation, you know, 2x plus 1 equals 7, and is x equals 3, you're wondering if that's a solution. Okay, and let's say that you didn't know how to like do algebra. You know, you would isolate you'd subtract 1 on both sides of this equation, isolate the x, you know, and solve. But let's say you didn't know that. Is there a way to confirm that x equals 3 is a solution to this equation? Is there a way to confirm that?
Yeah, we can substitute x with 3.
That's exactly right, Clea. We can substitute in, very good, x with 3. And 2 times 3 plus 1 does indeed equal 7. Oh, yes, it does. So this means then that x equals 3 is indeed a solution. So what's happening here with the differential equation is that they're telling you that y equals e to the rx power satisfies this differential equation. Somehow they came up with that solution, and you don't know why right now, but in the future you will. And as a matter of fact, well, if you take, how many have to take Math 282, differential equations? Okay, Mohammed has to, Masume, and you know, and Mohammed's taking linear algebra. I'm teaching that in the spring, by the way. I'm teaching linear algebra and multivariable calculus. OPME has to take differential equations. So yeah, when you take differential equations, you'll learn how they come up with. Okay, Mohammed, excellent. You'll learn how they come up with solutions like this, right? But for now, take it on faith. So, okay, what we're going to do to solve for R, what do you think we're going to do? What do you think we're going to do with this solution? Okay, Jonathan has a great idea. Let's take the first and second derivatives of this y equals e to the rx power, and then substitute it in the differential equation and try to solve for r. Okay, let's try that. So let's go to the next page. Okay, and let me blow this up here. Okay, so of course, if y equals, just I'm going to get my pen back here. If y equals e to the rx power, then y prime would be r times e to the rx power, and y double prime would be r squared times e to the rx power. And so I'm going to substitute in the differential equation. I'm going to substitute in what y double prime is, what y prime is, and what y is. And that's going to get me this equation here. Okay, let me give you a moment to catch up here. Please let me know if you have any questions. Okay, so here is y double prime, which is the second derivative of y is r squared times e to the rx power. Here is the first derivative of y, r times e to the rx power, and then here's y. And we want to solve for r. So there's a common factor of e to the rx in all three of those functions. So we'll factor it out, and this will give us e to the rx power times the quantity 2r squared plus r minus 1 equals 0. Now, this would imply, by the way, that either e to the rx power equals 0, or 2r squared plus r minus 1 equals 0, right? But if you think about this first statement here, e to the r of x equals 0. One moment, let me just draw a little graph here. I'm going to hold on, Clay. I'll hold that thought. So we know how exponential functions are, right? They're either increasing or decreasing. But do the exponential functions ever touch the x-axis? Do they ever touch the x-axis? They
No.
don't. That's right. So e to the r of x, that's right, Jonathan, that's right, Clea. So e to the r of x equals 0, that has no solution. So this means the only solutions are going to come out of this polynomial equation, 2r squared plus r minus 1 equals 0, which I have here. And it's a quadratic equation. We could use a quadratic formula, but it also factors into 2r minus 1 and r plus 1. Yeah, a question, Clea, question?
So the reason we like get rid of the e to the power rx is because it does not touch the x-axis, so there's no solution. That's why we just like take it off.
Right. Well, it's like if you have if you have like a times b equals 0, then either a is equal to 0 or b equals 0. So either in our case, e to the rx power would equal 0, based on this equation here. Either e to the rx power equals 0 or 2r squared plus r minus 1 equals 0. But e to the rx power equals 0, that has no solution. So the values for r have to come from this this polynomial equation. And when you solve it, by the way, you factor it, and then you set each of the factors equal to 0. You know how to do that. So r equals a half, r equals -1, and so the so that's what you're doing. Is that okay? Is that all right?
Yep.
Okay, very good, very good. Very good. Kind of separate this out here. So this means then that if r equals a half, y equals e to the half x power is the solution. And y equals e to the -1 over x is the solution because r can equal -1. So there are two solutions to the differential equation. Let me see. There was the zeros are a half. Mohammed, the zeros are a half, -1. But there's no, r equals 0 is not 0 of the solution. Well, see, e to the rx. So Mohammed's asking about this this part up here where I have e to the rx power equals 0. That has no solution. That has no solution. That just has no solution. So you can't get anything from that. Let me go to the whiteboard real quick here. I'll come back here. Let me go to the whiteboard. So let me kind of reiterate where I was here. So we agree that the differential equation, when we substitute in the e to the rx and its derivatives, the differential equation can be written like this. But this implies either e to the rx power equals 0 or 2r squared plus r minus 1 equals 0. Now, this here, 2r squared plus r minus 1 equals 0, would give you this. Okay, and so, r is a half, r is -1. But e to the rx power equals 0, this has no solution because an exponential function is never equal to 0. It's never equal to 0. E to the r, no matter what r is, your e to the rx would never equal 0. Because recall how exponential functions look, right? If you graph exponential functions, Yeah, yeah, they're, either they're increasing or decreasing, but they never touch the x-axis. All right, good, Mohammed, good, good. Okay, so now let's get back to the thing here, back to the, uh, okay, cool. All right, it's holding, that's interesting. So I guess it's holding the writing that I had. That's kind of nice. Um, but I think I can erase it now too. Okay, so we have two solutions to the differential equation, and the two solutions are e to the half x and e to the negative x. Okay, so there are your answers. This is what we call a second order differential equation because it had a second derivative in it. If it were a and notice there were two solutions. If it's a third order differential equation, you would see three solutions, okay, and so forth. So, but I want to be a little careful about generalizing on this. Wait till you get to Math 282 different. Well, Yonatan, in differential equations, you'll be dealing with differential equations of higher order. And the order of the differential equation determines how many solutions it has. But you can have what are called repeated solutions. Yeah, that's right. That's right. Um, so, yeah, you'll be seeing some really cool stuff in Math 282. I really encourage everybody to take that class. Um, okay, okay. Let us proceed on. Let's look at another problem. Okay. Okay, let me give you a moment to copy this example down, and then we'll talk about it. Okay, so let's take a look at this problem. So now here you have a population that's modeled by this differential equation. Okay, and so the PDT stands for something rate. It stands for growth rate. Growth rate of the population. Let's never forget a derivative is a rate. And the growth rate of the population is equal to 1.2 times P minus 1.2 times P squared over 4,200. And we're being asked a variety of important questions. So based on this differential equation that models the growth rate of the population, for what values of the population for what values of P is the population increasing? For what values of P is the population decreasing? And then what are equilibrium solutions? Okay, so let's talk about that. Let's talk about this. Let's focus on part A here. So when we say what values of P is the population decreasing, we really need to know where dp dt, and maybe let me just can clear a few annotations here. Well, you know, Yonatan, you're on the right track indeed, because remember, like in calculus 2, when you would have some function y, and you wanted to know where the function was increasing or decreasing, what did you look at for the function then? To determine where a function is increasing or decreasing, like if I say, hey, where's this function y increasing? You would look at the first derivative of y, right? And then you'd want to know where that first derivative would be what?
Concave up or concave down?
Well, that gets to inflexity, but for increasing or decreasing, we work with the first derivative. And that's right, Mohammed and Victoria. So we want to know where the first derivative is positive. Okay, so where does our function, increase, our function y, where the first derivative is positive, and where the function decreases is where its first derivative would be negative. Okay, well, there's no real difference. It's the same kind of thing here. If I want to know where my population is increasing, okay, I'm going to just try to find out where dp dt is greater than 0. And if I want to know where my population is decreasing, then I'm going to want to know where dp dt, where the derivative of the population with respect to time, I'm going to want to know where that is what? Where that is
Negative.
negative. Exactly. Good. That's right, Mohammed. That's right, Claire. And equilibrium solutions are where the derivative would
Equals 0.
equals 0. Because if the population's in equilibrium, that means it's not growing. That means it's not decreasing either. So, okay, the task is clear what we need to do. But to help us, what we're certainly going to do on the right side of this differential equation is we're going to factor out the common factor. And there is a common factor of those two terms. What is that common factor? That's right, Yonatan. Well, Mohammed, P is good, but we can do even better than that, 1.2 times P. So let me go to the next page here, and let's work through this step by step. So I factor out a 1.2 p from both of these terms, and I get then dp dt, and I'll write dp dt again here. dp dt is equal to 1.2 times p times the quantity 1 minus p over 4,200. Now, you know, p is understood to be a function of time. Population either grows or decreases over time. So dp dt then, you know, is our what we're doing here. And by the way, this differential equation, since the right-hand side here is a function of just p, it's what's called an autonomous differential equation. But we got to be a little bit careful, autonomous differential equation. We got to be a little bit careful because even though there's no like t on the right-hand variable in the right-hand side of the differential equation, p itself is a function of t. So in a sense, you know, there's a dependency on time, right? But really, all you need to know is what values of your population are to determine your derivative. So like for instance in part A, okay, well, so this factor here, let me just make it show here. Yeah, this part here, 1.2 times the population, that's always positive. That's always positive because you can't have a negative population. Okay. But this factor here, 1 minus p over 4,200, that can be positive or negative depending on what your population is. And so okay, well, it turns out then that if the population is, one moment, if the population is between 0 and 4,200, then that would make this second factor positive, okay, because you know, you could say, well, all right, when is 1 minus p over 4,200 positive? It would be positive when 1 is greater than p over 4,200, which means then that p would have to be less than 4,200. And so, yeah. So when this population, well, let's say it's a population of deer, when it's between 0 and 4,200, the population will grow because dp dt is greater than 0. Please let me know if you have any questions. Please let me know. Yes, Jonathan.
Professor, why is, like, I want to say limit, but that implies other things. Why is the cap of it being a population growth at 4,200? Like, I understand why when p equals 4,200, then it'd be 1 minus 1, 0, and that would go to 0. But what if it's not 0? What if it's over 4,200 and that becomes just a negative number? But a negative number would still work, wouldn't it?
Well, let's take a look.
Oh,
That's
no,
good. Let's go to part B. That's a good point. What if p were greater than 4,200? If that were the case, that would make this second factor here. Whoops, hold on. I don't know what that. Let me just clear the annotation. One moment. There's all kinds of new features here. This this second factor here will certainly be negative if p is greater than 4,200. And so if that happens, if P is greater than 4,200, then the derivative would be negative. And so the population would be decreasing with time t. In other words, populations, as you know, are not sustainable if they reach a certain amount, because there's limitation, for instance, on food availability. Okay, and so if population gets too big, in this case over 4,200, the rate of growth of the population would be negative, and the population would decrease. Okay, so now if the population were equal to either 0 or 4,200, then in that case, your derivative would equal 0, and that means if the derivative equals 0, the population stays constant with the time. So that, the derivative, like if you had y equals 4, and you said, tell me what dy dt is, you're going to say 0, right? Because y equals 4 is a constant function. The derivative of constant functions equals 0. And so, constant function, y equals 4, that's a horizontal function, right? That doesn't grow or decrease. So the values of 0 and 4,200 are equilibrium solutions for our population. Right? Are there any good questions on that? So the key was to factor that right-hand side of the differential equation. Now I'm going to show you a little picture here of what, some solutions, what solutions look like to the differential equation. Yes, Mohammed, question?
I put a question in the chat, but I was going to ask, would we be able to answer questions like this just by looking at the graph for it?
Well, it could be kind of difficult. I'll show you why. It's better to factor the right-hand side. I'd like you to factor the right-hand side. I'll show you why. I'm going to go to the next page if everybody's good. Okay, let's go to the next page. Here's the next page, and what I've done is I've drawn here some potential solutions for our differential equation. So let's restate what our differential equation is. Our differential equation, hold on here. Now, why is it doing that? Let's get this back here. Our differential equation is dp dt equals 1.2 times p times 1 minus p over 4,200. And so, like, for instance, let's say your initial population is 6,000. Well, if your initial population is 6,000, since that's over 4,200, population has to decrease. And it decreases until you reach this carrying capacity of 4,200. On the other hand, let's say your population is 1,000. Well, 1,000 is between 0 and 4,200. And so there, the population would increase. And it would increase up till you reach the 4,200 value. Notice that you have basically exponential growth in the beginning, okay, and then the growth, there's an inflection point, and then it calms down and settles to the equilibrium of 4,200. This is what's called a logistic model, and you'll study this more when you get to differential equations, Math 282. Naturally, if your initial population is 0, population stays at 0. And if your initial population of deer or whatever it is stays at 4,200, if it's 4,200, it's going to be stable there, no matter what, for all time. So you see, you're graphing here the population on the vertical axis. You have the population on the vertical axis and the variable t on the horizontal axis. So population is a function of time. But the growth rate of the population is dependent on the population at the time itself. And that's why we can draw these what are called qualitative solutions. These are all qualitative solutions for graphs of, I mean, we don't have a formula, right? We don't have a formula for the population, P of t. You know, P of t, we don't have a formula for it, but nevertheless, because we know the differential equation, we can graph typical solutions for the differential equation for different initial values of the starting values of the population at time equals 0. This is what's called qualitative analysis. Some differential equations, you can't solve them. You cannot solve them analytically, but you can still understand about their solutions by virtue of the fact that you have the differential equation. Okay, does that make good sense? Are there any questions on that? All right, well, if you're good, give me a thumbs up if you're good. Maybe give me a thumbs up here. Okay, Mohammed and Clea and Masume and John, wonderful. Good. And Niat, good. Lillian, how do you feel about this? Are you okay with it? All right, Lillian. All right, Helen, how do you feel with it? Helen? Good, excellent, excellent. Okay, okay. Well, let us proceed on. Let's look at one more example here. Let's look at one more example. So this is yet another example, section 7.1. Let me give you a moment to copy down the example.
Professor, was the previous problem also under 6.7, or is that a different section? I didn't notice.
The previous problem was section 7.1 also.
Oh, okay, sorry. Thank you.
No problem. You're welcome. Okay, so let's see what we have here now. So in this problem, we have a differential equation, and they want us to show that every member of the family of these functions is a solution to the differential equation. And we know that what we're going to do naturally is substitute in this function into the differential equation and show that it satisfies the differential equation. But why are they calling this a family of functions? Why are they calling this y equals the log of x plus a constant divided by x a family of functions? Why would that be? Well, there's something in this about this function that, and I'm hearing some answers here, but not quite the right answer yet. There's something about this function what's sort of unique about it compared to one function set you've seen in the past?
Isn't family function, from what we learned previously, that they're like similar in the form?
Well, and that's right. And Yonatan's noticing that we have a constant here. We have a constant. Hold that thought, Gabriel. Hold that thought. So you see, if you had just like y equals the log of x divided by x, that's just one function. But here, what we have is we have the y equals the log of x plus a constant divided by c. And the fact that we have a constant here, that constant could be anything. Constant could be 0, constant could be 1, constant could be 2, constant could be -1. There's an infinite number of values for that constant, and we could graph every function with all those different constants, and we get a family of functions. So a general solution to a differential equation is a family of functions. Just like for an antiderivative, the general antiderivative for an integral is a family. It's a family, right? I mean, if you have somebody noted here that, you know, if you have the antiderivative of x squared dx, that equals x cubed over 3 plus a constant. Well, so how many antiderivatives are there? There's an infinite number. It's a family, right? Because that constant could be any value. Well, the same here. This constant here could be any real value. But you're going to find that if we put in an initial, what's called an initial condition, if we say y of 2 equals 1, and what that means is when x equals 2, y equals 1. When we say that, you know, when we have that condition, then we're going to be able to solve. We're going to be able to find a specific value for that constant. You'll see what I mean. You'll see. So let's go ahead to the next page and do the first part. Show that every member of the family of functions is a solution to the differential equation. Here we go. Here we go. So, all right, y equals the log of x plus a constant divided by x. So I mean, again, my differential equation was x squared times y prime plus x times y equals 1. So I'm going to have to get naturally the first derivative. So okay, well I'm going to use the quotient rule here on this function. So that's what I do to get the derivative. And the derivative is 1 minus the log of x minus the constant over x squared. All right. Let's see if anybody has any questions on this. Lillian, do you have any questions on this?
No, not right now, honestly. I'm just watching.
Excellent, excellent. Mandy, how do you feel? All right, Mandy? Okay. All right, logged in but not here, I guess. I don't know. I'm going to call Mandy later. I have faith Mandy's with us. All right, so here's our here. What I do is I look at the left side of the differential equation. So x squared plus y prime plus xy. I'm going to substitute in. I'm going to substitute in the first derivative. Okay, I'm going to substitute in the first derivative, and I'm going to substitute in what the y is right here. And I'm going to work it out, and hopefully all that's going to equal 1 when I'm done. So of course, the x squared terms, okay, here and here go out, and the x terms here and here go out, and that's going to give me this. 1 minus log of x minus a constant plus log of x plus a constant, and we get a 1. Okay, so I have that in the recording. Let me go ahead, and I want to make sure people are copying that okay. And so therefore, we know then that this y equals the log of x plus a constant divided by x. It's a family of solutions to this differential equation. Okay, a family of solutions. Yes, Mohammed.
So how did you get how did you find out that it equals 1?
Well, are you okay going from this step to this step?
Sorry, which step?
So like you see how I substituted in.
Mm-hmm.
All right, so substituted in y prime and y.
Yeah.
To get us here.
Yep.
And then, I get down to here, and the constants cancel. And I have a negative log of x and a plus log of x. That cancels, and that gets me. Yeah.
Got it.
Good question.
Okay,
Good
thank
question. Sure, no problem. Are there any other good questions? Okay, so now we verified that that family of solutions is correct for that differential equation. And how do we get it based on the differential equation? You have to take Math 282 to see that. Okay. All right. Now, though, what we want to do is we want to add what's called an initial condition. Okay. We want to add an initial condition. Okay. Let me just put it in here. We want to add initial condition. Man, it's giving me a hard time. Come on. Let's get it. I want to add initial condition that when x equals 2, y equals 1. So when you have a different, I'm sorry, when you have a differential equation and an initial condition, that's what's called an initial value problem. And when we have that, we can find a specific solution. Let's go to the next page and I'll show you. Okay. So if we require that, I don't know why it keeps doing this. Come on. If we require that y of 2 equals 1, well, again, when, here was our solution to the differential equation. Y equals the log of x plus a constant, all divided by x. So, see, I put in the x here. That's an x, that's an x. And then over here, the y equals 1. Okay, so I substitute the x and y values in. It's really a coordinate, it's a coordinate. You're demanding that the solution pass through the coordinate 2, 1. X coordinates 2, y coordinates 1. And when you do that, it turns out that if you solve this equation, okay, it turns out that 2 equals the log of 2 plus a constant, and so the constant is 2 minus the log of 2, okay? And so the solution to the initial value problem then is equal to what you see down here. Exactly that. And there's that constant that you solve for. See, so you have a specific solution. And initial value problems have for basically well-behaved differential equations. Initial value problems will have unique solutions, like you see here. And if we had a different initial condition, we would get a different constant and a different specific solution. Are there any questions on that in general?
I understand when you like substituted 2 into the equation, but I don't understand how you got to that y equals at the bottom.
Oh, well, what I did was, okay, actually I got this on the thing. So you're okay that the constant equals 2 minus the log of 2, right, Mohammed?
Yep.
Okay, so I'm just going to then substitute that in for the constant in my family of solutions for this constant here.
Oh, okay.
And that's
That makes sense. I didn't realize that you were solving for the constant.
exactly. So giving me an initial condition allows me to solve for the constant. All right, very good question. Are there any other good questions? Okay, Mandy, how are you feeling about this? Okay, Mark, how about you? You feeling all right, Mark? Oh man, live. I hope some people are here. Nihat, how do you feel about this? Are you all right with this? Comfortable with this material? Okay, good, good. All right. Thank you, Nihat. Thank you, Zaina. Thank you, Franklin. Okay, Mark. Good, good. Just some more practice. I got you. I got you. All right, let me stop the recording.